Alrighty, let's start. There are some notes, but I've had to chain a PhD student to the photocopier. So when he, good man. When he's managed to get away from the lock, he'll turn up. Looking cool as well, actually. Give us off. I'm sorry they're stapled in the wrong corner, but the fact is, it's running. The photocopy is cleverer than I am. And more expensive. It's going to take a while. While that does its thing, so we'd arrived at this op-amp here, and it works just about. Well, that's not just about. It works completely. It's just that there are lots of things wrong with it, and we can make it a lot better. I don't propose to make my way through all this material today. I'm just going to go as far as I can. So we'd like to look at the three stages that we've got and try and find out how we can make them a bit better, or at least ameliorate some of their deficiencies. We have problems with the differential amplifier stage and with the voltage amplifier stage and with the output stage. And if you go back into the anatomy of the op-amp handout that I gave you a while ago, first or second lecture, they are all enumerated in there. And what I'm going to work through is essentially that, but in slide form. So slightly shorter words and explanations. So the first thing we can say is, well, half of the signal is actually wasted. We're only really interested in what happens to this resistor. And there is a signal current that passes in this line here that just goes into the minus rail. And we never see it again, it doesn't do us any good at all. If you go back to a very long time ago, you remember I had a diagram that had delta I here and delta I there, and it would be quite nice if we could get both the delta I's to do something interesting, as opposed to just let one escape. Another problem is that the balance of collector current is skewed somewhat. Ideally, we have the same collector current here as we've got here, but actually some current has to make this transistor go. So there's a slight imbalance, and we'd like to be able to deal with that. What is more, the current that has to flow into the base of this transistor and this transistor in order to make them go is quite large. When I say quite large, I mean the order of, I don't know, units of microamps to tens of microamps. And if you think about what I said regarding op-amp input impedances in EEE225, I said, oh, it's 10 to the 9 ohms or thereabouts. Well, if you've got microamps going in, 10 to the 9 ohms probably isn't going to happen for an input impedance. So we can act to make the input impedance a lot bigger. And this is good because it will load our circuits less and make the op-amp more ideal. The effective resistance that loads the differential stage is this in parallel with the input impedance of that. And the input impedance of that I derived last lecture, which is why I was going through all the little blocks, because we have to squish them all together now. And the squishing together just gets bigger and bigger and bigger. So as long as you understand the little blocks, you'll be able to make the biggest circuits you like. If you can't get the little blocks, don't even bother with this. It won't help. Go back and do the little blocks again. So we'd like to be able to make that resistance plus the impedance looking in there really, really big. And the reason we'd like to do that is the gain of the differential amplifier is proportional to GM and RL. And if we can make the apparent size of RL go up, we keep our GM the same, we'll get a bigger gain. Bigger gain is good because the forward path gain of the op-amp, open loop gain, we'd like it to be enormous. And that won't happen unless we actually design it to have a big gain. So the bigger gain is good. Bigger gain throughout. Happy? Not happy. Have you suddenly realised that actually the curve for learning is first year, or second year? And you're now on the turn, especially when it comes to mathematics. That's normal. So, problem with the voltage amplifying stage. We have to have a certain quiescent current flowing down here, and it has to be such that it will bias this transistor, give us the quiescent collector current we want. So we've got a voltage dropped across this resistor. That means that resistor, having had, it's got quite a large voltage dropped across it actually. Call that 0, 0.7 there, so we're plus 0.7 there, if that's 15, 14.3 across there? Yeah? Good, far too fast. Hear it again or not? Yeah? Righto. So assume no output, no current in the load, no current in the load, no voltage across it, because you've got Ohm's law. V is I times R, if I've got no I, doesn't matter how big a R I've got, that's good English, I won't have any V. No V here, so no volts, because that's at 0, no volts across there, that must be at 0 as well. If this is at 0 and this transistor is forward active region, little lie, but ignore it for now. 0.7 there to there, so this will be plus 0.7. Let's assume I run it from a 15 volt power supply because lots of op amps are run from 15 volts. That will leave us with 15 minus 0.7 across the resistor. Let's assume I choose between 2 and 5 milliamps in this, come on, amplifier lab. Choose between 2 and 5 milliamps. No? Still scarred, eh? The order of milliamps in this resistor, 14-ish volts across it, going to have quite a low value. We don't really want a low R here because this is the load for this transistor, and the gain of this transistor, or the gain of this amplifier block, is proportional to GM times RL, or RVA, or whatever I've called it. So making this resistance look really big is a good thing. The only trouble is we've still got to satisfy the DC conditions. So we'll have to come up with something to deal with that. If we make this really big and demand a large current through it, this node will drop in voltage to the point where this transistor never turns on, and then our op amp will work. Happy? Oh yes, output stage. So, things get even worse now, I'm afraid. There is a resistance looking in here, which is the input resistance of this transistor, and there is a resistance looking up there, which is the output resistance of this transistor, and they are related by the GM and beta of the transistor. If we adjust the load resistance, we will change the resistance that is seen looking into this transistor by virtue of changing its output resistance. If we adjust this resistor, making it bigger, we will adjust the resistance seen looking in here. If I was a signal attempting to get in here, sorry, it really does do it by itself. It's a question of the roughness of the board and the end of the chalk, and the chalk resonates. It's a second order system, it's got a Q and everything. So I'm going to drive a current, which should be red, in here, and I'll measure that well, let's assume I put a voltage in. I'll put in some voltage, VT, test voltage, and I'll measure this current IT, and then I'll say R is V over I, so I can know the input resistance looking in here. And when you're doing the amplifier lab, if you've done it, which most of you have now, you were doing a similar thing towards the end of day 3 when you were putting that 10 ohm resistor down. Really, we were not driving a voltage in, we were just loading up the amplifier so heavily that we could see the effect of the internal resistance. This is a much more mathematical way of doing it. So if we adjust this resistance, because this transistor is imperfect, we will see a change in the resistance we get looking in there. So these two things are coupled to each other by the parameters of this transistor, and the same is true for this transistor for the other half cycle. This transistor only deals with that bit, this transistor deals with that bit. if it's a sine wave. Okay, last one. We would like to put a little something in here. Battery. And we want to do that to spread the VB here and the VB here by 2 junction voltages. In order that you won't get, I can't make the screen go up, can I? In order that you won't get an output that looks something like this. Is that big enough? See, there's flat bits. If we can make these go apart by about 1.4 volts, we'll keep these transistors always turned on, and there'll be a small quiescent current that flows down there, which is what you were measuring on that analog meter in the amplifier lab, and adjusting the size of this voltage and looking what happens to the output resistance. Never mind the output resistance for now. I'm only interested in getting rid of what they call the crossover distortion. So these are the things we want to deal with. And we'll spend the rest of today, and however long it takes, working our way through them all. That's the crossover distortion. Oh, by the way, the tutorial sheet for all this innards of amplifier stuff is on the back of today's notes. It's only one question, but it's a good one. So, we have this crossover distortion, and we can put a voltage VB in between the bases there to spread them apart and get rid of the crossover distortion. Last lecture I talked about the magnitude of the signal current compared to the quiescent current, and that was to do with the class of the amplifier, and it also is reflected in the angle of conduction for each of the transistors. This is not separate. They both exist, but I'm just talking about them differently because I had to stop talking at some point. So there is no discontinuity. So what can we do about the input stage? We've got this business of current in here different from current in there, and we'd like to make them the same if we can. We can use a current mirror, which is the circuit on the board, just a 2 transistor circuit, and its job is to to adjust the current in T6's collector until it's equal to the current that flows in, well, it's equal to IL. It's not totally perfect, but it's actually very, very good. And we could expect 10 to 50 times improvement over a resistive load. So, to figure out what it does, assume that T6 and T7 are identical. That's to say, they have the same HFE and everything. And the circuit wants to make IL and I6 equal. And we've connected together the collector of T7 and its base. And we've connected together the emitters of T6 and T7, and bases are connected together as well. So both transistors have to have the same VBE. This applies to that one and that one. And IL would develop a sufficient VBE to cause a base current to flow here, which is both the base current for this transistor and the base current for this transistor. And the rest of this IL will end up going from T7 into the ground. So they've got the same VBE, and they're forcing the same, well, the base current will split evenly as a result of the VBE being the same. So we will end up with IC6 being equal to IL with the, well, negligible error, really. So if you want to know where to start with this, imagine that IL will make the voltage across itself, well, see the other end's grounded, so big as to force this current. And because these transistors are identical, we'll have 2 times IB, and the IBs will be equal. You say, how will it do that? It will make a voltage between this point and the ground, because we just, from a signal point of view, we'll take that around. A voltage at this point which is sufficient to force this current. This current will be forced by the VBE. So this thing will, so I'm going to put IL down this way, and it will make this voltage as big as it needs to. This voltage will connect to that voltage, so this voltage will rise, VB will appear, VB will appear and IB will flow. And when it does, we'll be in a state of happiness. Because the IB and the VB will be just about right to make IC7 flow. And a consequence of that happening, being that these two are the same, is that IB will flow and IC6 will flow. And because they are the same, IL and IC6 will be equal. Happy? It relies on the transistors being the same. Watch it back if you're not happy. We can do a little bit of maths, but I don't want to do too much maths because, if you do flip to the back of the notes, the maths is there. They're not for this bit, because I thought this one was sufficiently simple just to... But it's not simple. It's actually very difficult because you have to know where to start to think about it. If I said, we'll start at T6, what the hell will I say first? Nobody knows. I've got to know to start IL and think about what happens after that. So it's not easy. But I didn't want to write out any maths for all of it, otherwise we'd spend the rest of the course just talking about op-amps. So we have this current mirror. Happy with the operation? In that case, onwards. So we put the current mirror into the differential amplifier and we get the picture we have. We've still got RE at the top. That will disappear before too long as well. But for now we leave it in. And we can say, well, let us imagine that the base emitter voltage of T1 is slightly bigger than the base emitter voltage of T2. Another way of saying that is T1's base slightly bigger than T2's base, because we will measure the voltage between them, differential, one less the other. If it was an op-amp, like a whole op-amp, this would be V plus and this would be V minus. So this would be pin 3 and this would be pin 2 in an 8-pin package. This is non-inverting, this is inverting inputs. So this gets slightly bigger, which means that this bit gets slightly bigger. This is fixed, so the voltage across here gets slightly smaller, in fact, compared to the voltage across here, which means this transistor turns off a bit. The transistor turns off a bit, there will be a small reduction in the current which flows in its collector. We have IE over 2 because we assume IE splits evenly between them, especially now we've got a nice mirror at the bottom. As a consequence, the current that flows in T2's collector will increase by the same fraction, or the same small amount delta I. And T4 and T3's business is to make sure that IE over 2 plus delta I also flows here, because that's as we just described. Consequently, if we look at sum the currents up on this node here, we've got IE plus delta I flowing into T3's collector, and IE over 2 minus delta I flowing out T1's collector. So the missing chunk is delta I. If we flip back to lecture 3, where I started on differential amplifier, and I had the resistor here, we had only delta I over 2 at this point, flowing that way. We had delta I flowing this way. Now I've got minus delta I plus delta I. I've managed to get myself an extra delta I. If you're not convinced, go back and have a little look at lecture 3. In fact, I've got it here. I'll show you the difference now. Maybe. There we go. Make it bigger. So for this case, we've got the V plus increase. So it's the same arrangement. This has got slightly bigger. That's got slightly smaller. This current slightly dropped. Minus delta I, and the minus delta I is the only thing that ends up going that way on this wire, because this half goes straight in the ground. But now this half has ended up over here. So we have gained the delta I. This is really good. We can drive the bit that comes here, this bit, twice as hard for no extra effort. well, other than the current mirror. The same effect is true for signals. If we did this with all the small signals, we would arrive at the same. We'd have to replace all the HFEs by beta or GMVB if you prefer. The same is true. And that might even be on the next slide. No. Oh, it is, down there. No, it's all brilliant, fine, everything perfect. Not quite, actually. The mirroring isn't perfect, it does depend on the HFE, and even if you get two transistors that are made on the same day by the same technician, the same factory from the same wafer, having them doped with the same MBE machine, it still won't be the same. There will always be a little difference in HFE. Now I've assumed they're the same, and if you want to, you can go back and assign them HFE1, HFE2, HFE3, and just keep going, and then figure out what happens if they've got different HFEs. And if you do that, I will think you are super cool, which probably isn't what you want. But it is worth doing. Just, it won't come up in any exam or anything, but it will let you know that you definitely know what's going on. So we can get out of this difference in HFE a bit by adding a beta helper. And the beta helper is this transistor here. And its business is to make it so that the current that escapes from IL to drive these bases is mostly derived from DS in the ratio of IC to IB. So if we've got a HFE of 100 here, it will mean the current that escapes from IL to drive the two IBs will be 100 times smaller than it would previously have been. Happy? Good. That's all I want to say about that, pretty much. If you want to prove it, there's a little analysis there, and the HFE squared is the new thing compared to, compared to that one. If we had a small signal, we might have to worry about what the resistance looks like looking down here into this transistor collector. And the reason we might have to do that is because I said a while ago when I started that the gain of the differential amplifier is proportional to the GM and the size of this resistor. Now, sorry, T6, not T7. The size of this resistor. Now I've put a transistor in here and I need to know what the signal will see in terms of the small signal resistance looking into that collector. So we have to do some working out. HFEs become beta, and the thing that's really important is the early resistance of the transistor. Oh, there it is. So I'm going to arrive in a situation where I have this sort of thing. And really all I'm worried about is the fact that there's a little resistance RCE. So I draw it, I'm going to get rid of this one. I don't like writing over here because the camera's in the wrong place. I have my small signal transistor model. Collector, base, emitter. And I'll have a little RCE here. And that RCE is responsible for, you got that right? Oh, okay. Faster than me then. That RCE is responsible for the slope in the output characteristics. This changing gradient is modelled by that RCE. The RCE doesn't really exist, so I can't say it's responsible for. But, sorry, this is VCE, and this is IC. So, if I was a signal trying to get to the ground, I can't go through the current source, so the current source is deciding what it's going to get up to on its own. I'll be looking at RCE. So this RCE will produce a slight error. The currents will be doing the reflective bit between this collector of T, whatever it is, T2, T1. So there will be signal currents flowing in these two, and they will be reflecting the difference will be going that way, which is now double what it was before. And there will be a slight escaping current down through RCE. I will move on for now, but we can come back to it if you want. So this is the end of what I want to say about differential amplifier. We're going to, for now, we'll come back to what happens to RE later, but it's going away. The reason it needs to go, it's not strictly in my list of things to fix, but it exists anyway, so you may as well know it. If you make both of these go up together, it'll raise this node voltage, and if it does, there'll be less voltage for this resistor, and the current through our RE will drop, and we will adjust the GM of this stage because we'll have adjusted its quiescent collector currents. This is a common mode effect. We move these two up together or down together to make the current bigger. Whereas really we're interested in making this one different to that one. So RE is going to disappear in the end, but I don't want to talk about it until later. So we can have a look at this stage now, voltage amplifying stage. And the voltage amplifying stage is the main cause of imbalance between the different pair collectors. Because there is a little current that escapes down here to drive this transistor. That's its biasing current and a little signal current as well. But it's the biasing current we really care about. That's the DC effect, and the DC effect is the interesting bit. The reason we'd like them to be the same is when we work through it, we'll find that if we don't have balance here, we'll have a DC offset at the output. And you could say, oh, well, I'll put a capacitor on there like in the amplifier lab. Yeah, okay, you can. But if you wanted an amplifier to give you DC output, you'd want that DC output to, first of all, exist. If you put a capacitor in series with it, it will go away. Secondly, if I design a circuit and I know that under the correct conditions for a particular system this circuit's in, I should have 2 volts on the output. If I've got 1.995, that might not meet the specification. So I've got to make sure that I can define my DC output very accurately. And a whole class of op-amps exist where the designers have made extra effort to give very high precision, and they'll call it high precision, low offset, whatever. Good examples, OP77, for example. So we need to make sure that we've got balance here to force the DC offset to 0, or try to. Even then, in the amplifier lab, you had a little knob on the top transistor to adjust its DC offset. Remember? Yeah, remember. Good. So even with the op-amps in the amplifier lab are not good. The reason is we get through rather a lot of them now and then they do blow up. Through no fault of their own. I'll leave you to figure out whose fault it is. I blame the demonstrator. So even with the good ones, there is still usually a mechanism for you to tweak the balance of these currents. And we may or may not come onto it at some point. It's not particularly complicated, you can look it up on Google quite easily. So anyway, getting back to what's going on here, we've got to do something about the size of this current. It's far too large for what we really want. And we can put in the Darlington. Anybody familiar with Darlington? They used to teach it in GCSE electronics when I was doing my GCSEs. Right then, so the main cause of imbalance between these two is the current that escapes to bias this. And we can make that current considerably smaller by using this Darlington arrangement, which is on the board. In brief, if you looked at IBA and IE3, sorry, IB8 and IC, the total IC, you'll find that their ratio has gone up by the HFE of the two of them. So we'll end up with HFE squared. So IB is IC over HFE, and for this giant transistor all squished together, squared. IB is IC over HFE squared, assuming the HFE is the same, and that's approximately true. I think there might be some notes in your sheets, maybe. Yes, there is. Oh, small signal resistance. I didn't do the DC stuff. I didn't think it was worth the effort. Oh, it's actually on the slide. You look at equation 12, HFE8 plus 1, HFE3 plus 1 multiplied together times IB8 yield IE3. The plus 1s are there because I was talking about IC before. Now I'm talking about IE. And IE is IC plus IB, and IC is IB plus HFE. So I take out the HFE, HFE, IB plus 1. It's in the last lecture. Come on! Alright, if that's a bit too quick, IE3 is IC plus IB. That's ancient history. IE3 is therefore HFE3 times IB3 plus IB, so I've just subbed in HFE is HFE times IB is equal to IC into 8 to get 9. IE3 is then HFE times IE8 plus 1. The reason is IE8 and IB3 are actually the same current. Here, look at the diagram, you can see that there's one wire and they both flow in it, so they must be the same. Same logic applies to transistor 8. So we've got IE8 is HFE8 times IB8 plus 1. And then if you eliminate IE1, oh god, that's not IE1. Can't eliminate IE1, doesn't exist. You've got to get rid of IE8 from here and here. You might like to change that, sorry. Somebody send me an email to remind me, because otherwise next year I'll be standing here saying broadly the same mistake in the slides. Yeah, so eliminate IE8 from 10 and 11 to give you 12. And then we say that the usual thing we say about HFE, which is if HFE is much bigger than 1, which it almost always is, the IB is very, very small, so it goes away, to leave us IE3 is equal to IC3. And IC3 upon IB8 is extremely large. So if I had a transistor with a HFE of 100, my ratio of base current to collector current would be 100. And if I had two transistors in a Darlington, both having a HFE of 100, my ratio of my base and collector currents would be, for a biscuit, 10,000. Could you sense a biscuit was coming? Well, I'll have to. I know there's not much chance of biscuits in this. It's quite didactic. I stand up and talk at you guys. There isn't very much I can do about that with this material. It's just how it is. When we get to the, I don't know if we'll get to the end of this or not today, but if we do, I've got 3 op amps that I've chosen because they're some of my favourite op amps to go with my favourite transistors and other things. And there'll be lots of biscuits because you guys can just sit there and tell me what all the bits do. When I say there'll be lots of biscuits, I'm thinking maybe every time you don't know, I'm going to eat a biscuit. And every time you know it, that's right. No, I'm kidding. Right then, happy with Darlington. Darlington is now gone. What about for the small signal in Darlington then? Assume, now we could, if we wanted to, draw 2 transistor small signal models and bolt them together and write out some big long equations and try and figure it all out. And you can do that and you'll get an answer, and it'll probably be the right answer. Maybe. But when it comes to deciding which bits you can ignore and which bits you can't ignore, you'll have a hard time figuring out, because what you have is a big long equation, and you'll be sat there going, why does this term exist? What causes it? What happens if it changes by 10%? Will it make a big difference in the answer, or can I neglect it? And there are lots of ways of getting out. You can put some numbers in and see. You can sit and stare at the circuit diagram and think about it. It's much easier to try and boil the bits of the circuit down into the things that you know are important, and then operate on a much smaller circuit. So even though the circuit on the screen looks like a degenerated common emitter amplifier, kind of is a bit, but it's actually I've boiled the lower transistor, that's T3, down into just an R. And that's the input resistance of that transistor. And it's the only thing that I need to worry about. I'm not going to go into why that is. You must satisfy yourselves of that in a quiet place with a pad and a pen. So let's assume the input resistance of T3 is just R, and we draw the small signal diagram, so it's drawn, and then we'll add up the currents at the emitter. So I've got IB plus beta IB. I've decided to use beta. I decided that because I know it's going to be easier, and I know it's going to be easier because I already know this stuff. If you want to use GMVBE, you can, and it's a bit harder to do it, but it still works, and then later you can try it with beta and go, I was right. It is easier. I also know, because if you flick through textbooks and you find 3 textbooks that all use beta, you must be thinking, somebody knows something I don't. So then, once we've summed up the currents at the emitter, we'll have IB plus beta IB is equal to IE. And we'll take out IB and we'll have IB1 plus beta is IE. And then we'll sum up the voltages around the input loop. So we'll have VI is equal to VB plus VE. So it's only using loop and node analysis at the minute. And we're going to combine them in a bit to get a resistance. So if you go into the handout, you may as well flick through and make sure it's there so you know which one I'm talking about. I'm not going to work my way through it. That's why I give it as a handout, because there's nothing to be gained by me just standing there and talking maths at you. But it's there, and it's. I hope there are no errors. I hope. In brief, the input resistance, looking into. When I say input resistance, I mean the resistance looking in here. Input resistance looking into the Darlington is the RBE of T8 plus the beta of T8 times the RB of T3. The derivation is in the handout, and if you're diligent, you go through and prove it to yourself. That, I don't know if you've looked at last year's exam questions, but last year's exam question was on a Darlington, and it ran not quite along those lines, but similar-ish. So it's well worth the effort. This year's one will not be about a Darlington. I'm not that boring. Or will it? Who knows? I haven't written it yet, so even I don't know. Anyway, Ri is increased by the beta of the upper transistor, that's T8, multiplied by the input resistance of the lower transistor, which is RBE3. Now the quiescent currents in T3 and T8 will be different. If we go back up to here, sorry, I know you're looking at it, but IC3 and IC8 will be different. As a consequence, the GMs of those two transistors will be different, and as a consequence of that, assuming their betas are the same, which probably won't be, their RBEs will be different. So we can't assume the currents that RBE8 and RBE3 are equal to each other. If we could, that equation would become slightly smaller. You might have picked up that the equations in my slides are small, but the equations that turn up in the midst of it are bigger. I want to get back to a small equation, and I want to do that because in my head, it's important to know what's dominant and what doesn't matter. That's real understanding. Being able to do the maths is just a thing that gets in the way of everything else. Figuring out what's important and what's not is what will make you a brilliant circuit designer or sales engineer. Even worse, marketing. Not that I have any opinion on any of those matters at all. Right then, happy? Very unhappy. You want to hear this again? Yes. Alrighty. So, we are working out the current looking into this node and the voltage on that node, and we're going to divide one by the other to end up with an equation for the resistance looking in. So we use R is V over I in the end, which is one of the last lines in the handout that I give. So I'll sum up the input loop, so I'll sum up the voltages around this loop here, and this VI is VV plus VE. And I sum up the currents on this node, and I've got this current and this current coming in, and this current leaves. So I've got I is equal to that plus that. And then I do some jiggery pokery, which is in the notes. And I haven't even got a copy. Let me steal yours for a minute. Oh, you've got it there. Oh, you've got two sets. This is mine. Well, what do I do? So that gives me one, well, it gives, 1 is the sum of the currents, 3 is the sum of the voltages, 2 is just a change around of the currents. I make the currents into volts over resistance, so V over R is I, if I'm still in currents. And then 3 through 9 is me buggering about a bit with the equation for the voltage loop. And then I put GM in, and then out pops the answer. Any better? Not really. The trouble with this sort of thing is I can't beam it in. You've got to give it a go. If you can't do it, you can come see me. Well, the best thing to do is drop me an email, because the chances of you finding me in my office, almost nil. It's like finding an electron in the conduction band at 0 Kelvin. Not happening. And that will make the semiconductor highly resistant, won't it? Good. I dare not offer biscuits for semiconductors, people think something's wrong. Right then. Can we move on? In that case, next thing we've got to worry about, probably last thing for today, size of this resistor. Earlier I said, right in the beginning, I said a current flows through here and there's quite a big voltage across it. 0 and the output, assuming there's no input, plus a 0.7 to get to there. That's at plus 0.7, so that's if that's 15, 14.3 across here. I choose a current to flow down there in the order of a couple of milliamps. This won't be more than a few hundred ohms, kilo ohm or 2. Not a very big R. And the reason I need a big R is because the gain of this stage is GM RL, more or less. If I've got a small RL, I haven't got very much gain. And I'm calling this the voltage amplifying stage. So it's got to do some voltage amplifying, otherwise it's not going to be any good. I can put a circuit in here involving a transistor to choose this current that will flow in this pathway and yet maintain only a small voltage across it. And this will be a current source. That is to say, I will try to manufacture one of these. Not a dependent one, this depends on the value across there. I will try to manufacture one that I can control with the resistor or a potentiometer or something else. And the circuits I end up using is this one, which is more or less the simplest that you can, okay, there are simple ones. This is the simplest reasonable performance one. Still lots of problems with it, but I won't go into them. The way it works, anybody for a biscuit, say how it works. 2 biscuits. This is now just a game where I see how much biscuits it takes to make you guess. 3 biscuits. Just make biscuits a currency and check out. It's pretty much in front of you. So we've got this bias involved with VB, and VB is going to fall across the VB of the transistor, B for biasing, or B for base, whatever you prefer. We'll have a 0.7 to turn on this transistor, and we'll have a resistance RE, which will be the thing that sets the current. So if we sum up the voltages around this loop, we'll have VB must be to 0.7 plus the voltage across RE, which is essentially what I've got there, but written out slightly differently. So I can choose my RE, and I will get a current out of IC, which is very, very nearly equal to the current in RE. The difference being that RE must be IB and IC. If you don't feel happy with PNP transistors, good excuse to practice. Which way does the base current go? Outwards. Now have biscuit for outwards. Just in case you didn't see that, the answer is it travels out of the base and goes that way. If you're wondering, does it go back up here? The answer is no. I need to put in a little circuit under here, which is probably just a resistor to ground, to bleed that base current off somewhere. It can't go back up here because as far as the current here is concerned, this is at a higher potential, and the current will never flow towards the higher potential. Did I give you a biscuit? God, what have you got? A what? Gum. Oh, all right. whatever. So we've got to think now about, I've got some signals down here, because what I've really done is I've inserted this circuit in this space. Oh. Yeah, that's not a very good drawing. There's my resistance. This one is not on the diagram, but it's for the base current to do that. You could, if you wanted to, tie it to the negative rail. You'd just end up with a bigger voltage across your resistor, so you'd have to have a higher power dissipation resistor for the same job. Is that sufficiently clear, or do you need to be bigger? Is okay? Right. Somebody at the back says it's okay, so it must be all right. So we've got a signal here, and that signal will pass straight through this source, which I haven't actually talked about yet, but if you prefer, you just call it a wire, that's fine. All it means is these two will be tied together. And this signal will see something in the collector of this transistor. And we've got to worry about what it sees, because whatever it sees up there will be our new load resistance. And that's the thing that will determine the gain along with the GM. So we need to work it out. But there's only 2 minutes to go, and I think I can save it. Can you wait? Are you sure?